Hey, and welcome. Today, we're going to pull back the curtain on the internet itself. We're talking about the invisible highways that power our entire digital world, and, more importantly, the AI that's being built to actually pilot it. So let's get right into it. First things first, let's get one thing straight. The internet isn't some magical cloud. It's a real physical thing. You should think of it like a massive global superhighway system. But, instead of cars, it's moving data. And the roads? They're these countless strands of glass, each one thinner than a human hair, zipping our information across the globe as tiny pulses of light. But here's the problem. With all the streaming, the remote work, and just everything we do online, this superhighway is getting unbelievably crowded. It's becoming super complex. And the old school, manual ways of directing all that traffic, they're just not cutting it anymore. So what do? How do you manage a system that's just too fast, too big, and way too complicated for any human to handle? And that really gets us to the heart of the issue here. We're all demanding more and more capacity, right? And we expect it to be perfectly reliable all the time. That constant pressure is pushing the old ways of managing these networks, well, pretty much to their absolute breaking point. Let's bring this down to earth for a second. Think about it. That movie you streamed last night, the video call you were just on, even the photos you just uploaded. Every single one of those bits and bytes was turned into a tiny flash of light and blasted through these fiber optic cables. It might have traveled thousands of miles in just a fraction of a second. The sheer scale of it all, it's just staggering. Okay, but here's the catch. Sending a pulse of light down a tiny glass thread for thousands of miles, it's not a perfect process. Along the way, that signal starts to degrade. It gets distorted. The best way to think about it is like static on an old radio signal, but for light. This storm of distortions is, without a doubt, the single biggest headache in optical networking. And this right here just shows you the problem perfectly. See that? You start with a clean, crisp, perfect pulse of light. That's how it leaves the station. But by the time it arrives at its destination, look at it. It's all distorted and noisy. And that noise is exactly what causes your slow connection, or a dropped call, or that pixelated video stream. So the million-dollar question is, what's actually causing all this distortion? So it turns out this degradation, or impairments as the experts call it, basically falls into two main camps. First, you've got linear effects. An easy way to think about this is like a race where different colors of light are the runners. They all start at the same time, but they travel at slightly different speeds, so they arrive all smeared out. Then you've got the really tricky ones, the nonlinear effects. For this, imagine a speaker turned up so loud that the sound itself starts to get distorted. It's kind of like that, where the sheer intensity of the light signal starts messing with itself. Okay, so how in the world do you fix problems that are this complex? I mean, you can't just send a technician out to check on 1,000 miles of cable, right? So instead, we're bringing in a team of what you could call digital specialists. We're talking about a whole suite of machine learning models that are designed to diagnose, predict, and, this is the key part, prevent these failures before they even happen. First up on our AI team is the decision tree. This model is like a super logical diagnostician. It just follows a simple flowchart. It looks at the data and asks a series of simple questions. Is the power level too low? Yes or no? Is the signal-to-noise ratio okay? Yes or no? By going through this checklist, it can just, boom, rapidly pinpoint exactly what's going wrong. But some problems are a lot more subtle than that, and that's where the next specialist comes in, the neural network. I love this analogy. Think of it like an expert radiologist. After seeing thousands and thousands of scans, they just develop an intuition for spotting weird anomalies that a simple checklist would totally miss. That's what this model does. It learns these incredibly complex patterns of signal decay all on its own and can predict problems without anyone having to tell it what to look for. And believe me, the team doesn't stop there. You've got the random forest, which is basically a whole committee of these diagnosticians all voting on the problem. This makes its predictions super accurate. Then you have something called network kriging, which is kind of like a geographic profiler. It can figure out the health of parts of the network that aren't even being monitored, just by looking at their neighbors. And then you have GANs, which are totally fascinating. It's like having a master forger and a detective working together. They learn what normal looks like so perfectly that they can spot even the tiniest, rarest failures. All right, so we've got this awesome AI diagnostic team. But where do they do their work? They operate inside the next and maybe most important layer of this whole solution, the digital twin. This is, and I'm not exaggerating, one of the most powerful ideas in modern engineering. The best way to picture it is as a perfect real-time flight simulator. But instead of a plane, it's for the entire internet. So what is a digital twin exactly? Well, it's a dynamic virtual model of the physical network. And this is key. It's not just some static map. It's a living, breathing replica. It's constantly getting fed real-time data from all the actual hardware out there, so it mirrors what's happening in the real world second by second. And how does it actually work? Well, it's basically a three-step loop. First, you've got real-time monitoring, just constantly pulling in performance data from the live network. Second, that data is used for what's called mirror modeling. That's where you build the accurate virtual copy. And then, finally, this is the magic part: automatic control. This is where you use that virtual model to safely play out what-if scenarios and even automate fixes. But there's a big hurdle. Before you can build that perfect virtual mirror, you have to deal with the raw data. And real-world data is, well, it's messy. It's coming in from thousands of different devices in all kinds of different formats. That's where this data fusion pipeline is so critical. It's like a super-powered cleaning crew. It takes all that chaotic raw data and cleans it, labels it, and standardizes it, turning a huge mess into a pristine, reliable source of truth that the digital twin can actually understand and use. And this is why the whole concept is such a game changer. Just like a pilot practicing in a flight simulator, network operators can use the digital twin to test out pretty much anything. Want to see what happens during a massive traffic spike? Simulate it. Want to practice responding to a huge hardware failure? Go for it. You can do all of this without ever touching the live network. You can fine-tune things and find the best solution without any risk of causing a real-world crash. Okay, so let's zoom out for a second. We have an elite AI diagnostic team working inside a perfect digital replica of the network. Where is all this heading? What's the endgame? The ultimate goal here is a truly self-driving network, an internet that can manage, heal, and optimize itself all on its own. And the final piece of this puzzle? Well, it's the same kind of tech that powers things you've definitely heard of, like ChatGPT. We're talking about large language models and what's called agentic AI. These things act as the central brain, the expert pilot in the cockpit. They can understand a command given in plain English, use the digital twin to reason about what's going on, and then tell the whole AI toolkit exactly what to do. So when you put it all side by side, the difference is just night and day. The old way of managing the internet's backbone, it was all manual, it was reactive. You basically waited for something to break, and then you'd spend hours, maybe days, trying to figure out what went wrong. This new vision is the total opposite. It's all driven by AI, it's proactive, it's predictive, and it's capable of healing itself, often before a human even realizes there was a problem in the first place. So why should you care about any of this? Well, the answer actually affects you every day. It means fewer of those super frustrating service outages. It means your video calls are more reliable and crystal clear. Your streaming is smoother. On a bigger scale, it means a much more resilient global internet that can handle, well, pretty much whatever we throw at it. And it means cool new services can get rolled out a whole lot faster. And all of this leads to one final, pretty mind-bending thought. We're on the verge of building an internet that can literally heal itself. But what comes after that? Could this tech lead to an internet that's so smart it can actually anticipate our needs? Imagine a network that reconfigures itself automatically for a huge global event or a new viral app before we even realize we need the extra capacity. That is the future we're talking about here.